All right, let's dive into the world of compiler testing and optimization. I found this research paper that uses large language models to uncover hidden inefficiencies in how compilers, shrink code size.
Yeah, those LLMs, like the ones behind chatbots, it's pretty fascinating stuff. They're tackling a problem that's been around forever in software development.
Right. And it might sound kind of technical, but it really affects everyone. Think about it. Faster apps on your phone, more efficient systems and everything, cars to spacecraft, even longer battery life. And get this, the researchers actually found real bugs in some widely used compilers, like GCC and LLVM.
Oh, yeah, those are like the big names in the compiler world, right? They're responsible for translating code for a ton of applications.
Exactly. Okay, so before we get into how they actually used LLMs, can we just step back for a second? What makes compiler testing so tricky? Because it's not just about like checking if the code works, is it?
You got it. Compilers are super complex. It's like they're master translators. Not only do they have to convey the meaning of your code, but they also got to make that translation elegant and concise. You want optimized code, not just code that works.
So it's like imagine translating a book, right? You don't want a clunky word for word thing that misses the beauty of the original. You want a translation that's both accurate and streamlined.
Perfect analogy. We call that extra bulk code bloat in the compiler world. It's like having a suitcase full of stuff you don't need weighing down the whole system. And that can lead to, well, slower performance, eating up more energy, even problems for devices that don't have a lot of memory.
Okay, I see the problem. So traditionally, how have developers tried to deal with this code bloat and make sure compilers are doing their optimization magic the right way?
Well, one way is random program generation. There are tools like CSmith that basically just throw a ton of randomly generated code at the compiler to see what sticks, like a stress test.
Oh, okay.
The catch is, though, these tools need a ton of handwritten rules and constant updates. Programming languages are always changing, so it's a lot of work to keep up, like trying to hit a moving target.
So that's where LLMs come in, and that's what makes this research so cool. Using AI, which we normally think of for text, to improve code efficiency. That's pretty counterintuitive, right?
It is, and that's what's so innovative about it. The researchers didn't use those handcrafted rules. They gave the LLM a basic program and told it to basically mutate it, to add complexity step by step.
So they let the LLM play with the code a bit, but with some structure.
Exactly. It's like giving it instructions. Add a loop here, make this condition more complex. That way they could get a bunch of different test cases without writing tons of code themselves.
And I read that the whole system only took like 150 lines of code. That's crazy compared to those other tools that need tens of thousands of lines. But hold on, how did they use these LLM-generated programs to actually find optimization problems? Were they looking for crashes?
It's a bit more subtle than that. They use something called differential testing. Basically, they ran the same program through different compilers or even different versions of the same one and compared how big the output code was.
Oh, so like a race between compilers, if one spits out much smaller code, that could be a sign of missed optimization.
Exactly. And they had four main types of this differential testing. One is dead code testing, which focuses on whether the compiler can get rid of code that never actually runs.
Like finding clothes in your closet that you never wear anymore, just taking up space.
Yep. Dead code should be easy for a compiler to clean up, but sometimes it misses it. And this test is cool because you don't even need to compare different compilers. You run the same program through the same compiler twice, once with optimizations on, once with them off. Any difference in size could mean there's an issue.
Wow, so even one compiler can have its own problems with optimization. Nobody's perfect, I guess.
Definitely. Another method is called multi-compiler testing. This one compares how different compilers deal with the same code. That can tell you a lot about their strengths and weaknesses.
Oh, so it's like a compiler showdown. Which one's going to make the best code? I'm intrigued. Did they find any big differences using this?
Yeah, they found some pretty big differences. Like in some cases, one compiler missed an optimization that another one caught. They even found a 36% code size regression between GCC 15 and GCC 14.
Whoa, 36%. That's huge. So an update to the compiler actually made it worse at optimizing. That seems kind of backwards.
It does, but remember, compilers are super complicated. Sometimes a fix for one thing can accidentally create another problem somewhere else.
Makes sense. So this multi-compiler testing, that's a really good way to find those problems, huh? But were those discrepancies just like theoretical, or did they actually find real bugs in these compilers?
They found real bugs. They confirmed 24 bugs across a bunch of compilers like GCC, LLVM, Rust, even Swift.
So this wasn't just, a thought experiment. These are bugs that could be affecting software we use every day. That's a little unsettling.
It is. These compilers are used to build so much of the software we rely on, from phones to critical infrastructure. Even a small bug can have a big impact.
Okay, so what kind of bugs did they find? Ones that might actually affect us.
Well, one interesting one was a bug where a compiler didn't eliminate a dead loop.
A loop that's just spinning and spinning and doing nothing. That's a lot of wasted energy.
Exactly, and that can slow things down, even affect battery life.
So a compiler bug could be the reason my phone dies so fast. Who knew?
It's definitely possible. Another one involved different versions of GCC making very different size code for basically the same program.
So one version was way better at making compact code than the other. That shows how important testing different versions is.
Absolutely. So this whole approach with LLM seems really promising, but did they run into any problems using these large language models? It's still a pretty new technology.
Yeah, that's what I was thinking. AI generating code, I bet it doesn't always go perfectly.
You're right. They did have some quirks. About 3.55% of the time, the LLM made code that just wouldn't compile.
Really, the AI that's supposed to make good code sometimes makes bad code. What kind of errors were they getting?
Sometimes it was simple things like a missing semicolon. Other times it was more subtle, like the LLM misunderstood what it was supposed to do.
So it wasn't a magic bullet. They had to figure out how to deal with those AI hiccups. How did they make sure the code from the LLM was actually good for testing?
They had to get clever. For example, they'd check if the code size increased like it should as it got more complex.
So if the code gets more complex, the size should go up too. That makes sense. If it doesn't, something's probably wrong.
Exactly. They also use tools called sanitizers. They're like spell checkers for code, catching errors before they cause big problems.
Ah, okay.
Those sanitizers helped make sure the code was good and wouldn't mess up the testing. Now, this research focused on C and C++. I wonder how easy would it be to use this for other languages? There are a lot of them out there.
Right. Would they have to start over for each one?
Actually, it's surprisingly easy. They used an off-the-shelf LLM in tools that are already out there. They even showed how they could adapt it to Rust and Swift.
Oh, interesting. Those are very different from C and C++I. Did it actually work?
It did. Within just an hour of testing for each language, they found one bug in Swift and four in Rust. Real bugs affecting code size and how well it was optimized.
An hour. That's pretty fast. What were the bugs like in Rust and Swift?
Well, one of the Rust bugs was with nested loops. The compiler should have been able to simplify them, realize the answer would always be the same, but it only did it partially, and then used a technique called vectorization, which actually made the code bigger and slower.
So it's like the compiler took a long detour instead of the direct route.
Yeah, exactly. The Swift bug was a case where the compiler didn't realize a nested while loop was actually dead code. It would never run.
Ah, more sneaky dead code. Why didn't the compiler catch that?
Sometimes the code's logic can be tricky. The compiler might not have enough information to know for sure if a piece of code is unreachable. In this case, though, removing that dead loop actually let the compiler simplify other parts of the code so it ended up smaller and more efficient.
So even a little dead code can have a big impact on how efficient things are overall. What about the other Rust bugs?
The other ones were a bit more technical. It was about how the compiler made instructions for different types of processors. But the point is, even in newer languages like Rust, there's still room to make compilers better at optimization.
It seems like we're always searching for that perfect balance between making code run fast and making it efficient. And using these LLMs, we've got some really powerful tools to help us with that now.
Exactly. This research isn't just about finding bugs. It's about figuring out how to make compilers the best they can be and really understanding how they work.
So what does all this mean for software in the future? Are our apps going to suddenly become super fast and efficient?
Well, maybe not overnight, but this research opens up a lot of exciting possibilities. Imagine AI helping us write better, more efficient code, finding security problems, even designing entirely new programming languages that are perfect for certain jobs.
That's a pretty amazing vision of the future. It sounds like AI is going to be more than just a tool. It'll be like a partner in software development.
Absolutely. And this is just the beginning. We have a lot to learn and explore in this area. Who knows what breakthroughs are waiting for us as we keep pushing the limits of what we can do with AI and software.
It's definitely a fascinating time to be watching all this happen. And for everyone listening, if AI can help make our software more efficient, what other impossible things might become possible? What other inefficiencies are hiding that we can fix? There's so much potential. Thanks for joining us on this deep dive.